In Section 3 of the Solutions worksheet, we look at acid-base reactions. In number 1, we're asked to identify whether each species is a Bronsted acid, meaning a proton donor, a Bronsted base, a proton acceptor, or both, meaning that it's amphoteric or amphoprotic. Letter A, phosphate, is a Bronsted base. It does not have a hydrogen to give up, but it could accept a hydrogen. Letter B is also a Bronsted base. The chlorite ion can accept a proton, but it does not have one to donate. Letter C, ammonium, is a Bronsted acid. It has a proton that it can give away. And in letter D, this is both, meaning amphoteric. And if we look at what we get in each situation, letter A, if it accepts a proton, we'd get HPO42 minus. In letter B, if it were to accept a proton, we would get HClO2. And letter C, if it were to donate a proton, we'd be left with NH3. Letter D, if it donates a proton, we end up with the carbonate ion. And if it accepts a proton, we end up with hydrogen carbonate. Next, we're asked to create balanced equations showing the neutralization of each acid and base. Remember, it's important to look at whether they are strong acids or strong bases so that when we create the ionic equation, they're written appropriately, and then the net ionic equations follow. In letter A, we have acetic acid, which is a weak acid, combining with potassium hydroxide, which is a strong base. Our reaction would produce potassium acetate, which is aqueous, and water, which is our liquid. In the ionic equation, we showed that acetic acid largely stays together, but the potassium hydroxide dissociates into potassium ions and hydroxide ions. After the reaction, we have potassium acetate, which exists as ions, and water, which exists as a molecule. If we look for the spectator ion, the only one we'll find is potassium. So eliminating the spectator ion, we have acetic acid plus hydroxide yields water molecules plus the acetate ion. In letter B, we have again a weak acid with a strong base. Our carbonic acid is weak. Sodium hydroxide is the strong base. They react to create sodium carbonate and water. In the ionic equation, we show that carbonic acid exists mainly as the molecule, but sodium hydroxide exists entirely as ions. On the right-hand side of the equation, our sodium carbonate exists as ions, and our water as a molecule. Look for your spectator ions, and it appears that only sodium is a spectator ion, so if we eliminate it, we get the following net ionic equation. Carbonic acid plus hydroxide yields water plus carbonate. And in the last one, I have nitric acid and barium hydroxide, both strong electrolytes. Nitric acid exists as ions, as does barium hydroxide. On the right-hand side of the equation, we get barium nitrate and water molecules. And we can write the ionic equation showing that on the left side, everything exists as ions. And then after the reaction, barium and nitrate exist as ions, and the water molecule exists together. We could then separate this into our net ionic equation. We could get rid of barium and nitrate since they're both spectator ions. And we have 2 hydrogens plus 2 hydroxide yields 2 waters. We could simplify this as just hydrogen ions plus hydroxide ions yield water molecules.